Hi, I'm Mathis. I work at Funkwerk, where we develop passenger information systems for trains. This means that we need to take in data from a wide variety of sources in a wide variety of formats and make it work together in a halfway unified domain model. So in order to reduce complexity overhead, we are using microservices to separate development between different requirements of different interfaces and different business processes. And so we've recently open sourced our library Serialized. The dlang link is in the description. And if you're also interested in developing microservices, you're probably going to find it useful. One thing that's core to microservices is that you have a bunch of processes and you want to just pass data between them, usually in the form of a remote procedure call or a REST call. So usually when you're communicating with an outside system, you need to massage the data into a specific form. But internally, you usually don't care about format so much about consistency and ease of use. You just want to take some struct, or you take some array and throw it out in process A and just get it back in process B. And you preferably don't want to worry about anything that happens in the intermediate in between. So what I'm going to do is to demonstrate what I'm talking about. I'm just going to throw up a code window here, and I'm going to initialize the repository and throw in some data types that are sort of typical for the sort of domain types you would usually encounter in a program. Now, the classic way to encode this into a JSON value would be to do something sort of like this, right? Encode this into a JSON value would be to do something sort of like this, right? And so that we're seeing that this is unsatisfactory in a lot of ways. For one, it names every single field multiple times. It's very redundant. For another, it concerns itself with protocol logic, which is always kind of annoying. It's a bit spammy. We're looking at specifying a lot of types here that we frankly should already know. And to be honest, this is the sort of thing that templates were invented for. So let's replace this with the standard boilerplate template, nothing complicated. And we can see that it just dumps our internal type out exactly as the type suggests. So each field is serialized with that field's name, and each more complex type is recursed into arrays are arrays, structs are structs. It's very basic. So you may have noticed that we were using boilerplate there. Why are we using boilerplate? Well, there's two aspects of it. The first is that it lets us get access to private fields as long as they have an accessor, and as long as they are being generated by the constructor that boilerplate generates for us. For context here, boilerplate is my utility library to automatically generate constructor for all fields, generate possibly accessors, generate invariants, generate a toString method for all fields, and so on. And so the second aspect of it is that when we are talking about serialization, what we are actually doing is we are executing a remote procedure call to a constructor. So there may be fields in there that are not relevant to us that we are generating in the constructor with a new or with some sort of caching. And for those fields, we don't want to send them on the wire. We just want to send exactly what we need to call the constructor and get an equivalent data type out on the other end. So boilerplate helps us do that and discover the fields necessary to do that. Right. So now that we have this type and we have this very easy solution, let's actually make it a bit more complicated. And what we see is that the encoder complains that it doesn't know how to encode a UUID because we haven't given it that capability. But So the classic way to do that would be to annotate either the field or the UUID struct itself with a user-defined attribute that describes how to encode it. And that's cool for types that we control, but at Funkwerk we really can't do that even when we want to because of our code layout. So basically we've split our code base into 3 layers, approximately domain, application, and infrastructure. And you may remember this from last year when we called it model, control, and protocol, but the names don't matter. The point is that we cannot have JSON encoding in our domain layer because the domain layer is not concerned about wire format. It's not concerned about how we are supposed to move this data type from A to B. And you'd think that a user-defined attribute would be a very minimal incursion, but you cannot get this sort of thing through review. And believe me, I have tried repeatedly. But hey, constraint breeds creativity. So the first thing here is that we need to have the encode function in a separate file. We need to have it in the infrastructure layer. And we need to have it not at all touching into the domain layer. So I'm just going to whip this up here. And what we're going to do is we're going to take that encode function and we're going to pass it to encode JSON as a second parameter. And now you may wonder, how are we going to do this when there's multiple functions? Well, the very easy and convenient solution in D is that you can actually pass as many functions as you like to a single template parameter, as long as they have the same name, because you can pass an entire overload as a single parameter, which is incredibly convenient. So in the backend, Serialized will just look if it can call the encode function with any type that it doesn't know what to do with. Actually, it will give the encode function priority, so it will check if the encode function matches int, float, which it doesn't, and then UUID. And so when we run this, we will see that so what happens is that our UUID is serialized to a string, and this is packed into a JSON value, and we just need to worry about this one type at the leaf of our type tree, and we don't need to worry about anything else because the templates Serialized will handle all the other types on its own recursively. And so now we are running into a second problem, which is what if we want to change the name of a field in a type that is not a leaf type. So for instance, if we wanted to change every in domain type into children. And so there's a second approach to doing this that I'm going to talk about sort of parallel to the existing one, and it's to use domain transfer objects. Now, the idea about domain transfer objects is that we have complicated internal types. There may be classes, there may be hash nibs with complicated keys, but we can usually describe them in a way that is simpler for the encoder to digest. And so we call these types domain transfer objects. So that's types that are used to transfer domain objects between systems. So you have this tree of domain types, and then you have an adjacent tree of domain transfer objects that are created from the domain tree with transform functions. So I'm going to code this up as well, and I'm going to show you. Oh, I'm an idiot, yes. Right, so we see that this works the exact same as before. And at this point, you may be wondering why I introduced the encode parameter only to make it immediately useless. And well, I'm going to come back to that. For now, what I wanted to take away from this is that we can use domain transfer objects in order to encode our domain types into a form that is easily serialized. And we don't need to worry about annotations at all, because everything that we have internally can be easily represented unambiguously in our wire format. Well, for JSON, but not for the other supported output format, which is XML, which brings me to my next point. Please stop using XML already. Okay, so what makes a good serialization format? The basic premise of a serialization format is that you can easily take a data structure in your program, usually some internal representation, and turn it into a wire format and unpack it. Now, you can debate about whether the representation should be efficient or it should be readable. That's fairly open. There's formats for both cases. The important part is that they're unambiguous, forward-compatible, and simple. How does that look in practice? Well, one example for unambiguity is what you would call structs and arrays, right? Your daily bread, your typical internal data formats. So you have arrays, that's a homogeneous list of values, numeric index, always the same type. And you have structs, so that's a mapping of string keys, usually string keys or something that can be represented as a string to values of different types. And this is as close to universal as you can get. For one, because basically every modern programming language has structs and arrays as built-ins. C has them, Java has them, D of course. But also because every serialization format has them as primitives. JSON has structs and has objects that's structs and has arrays. HDF5, if you know about that, it's a serialization format for scientific data. It has effectively structs and arrays. It has compounds and arrays, which are effectively the same thing. If you look at protobuf, it has message, it has repeated. That's, again, structs and arrays. So then you come to XML, and XML has elements, tags, I guess, and it has attributes, and it has text as a fundamental primitive. So I guess if you have an object, you represent it as a tag. So it has the tag has keys, and those keys are your fields, which are encodable as strings, except sometimes not, sometimes they're children. And your arrays are just completely flattened out as subtags. So if something is in an array, then it can't be an attribute, so it has to be a subtag, has to be a sub-element. And I guess string serializable fields, I guess there's one privileged field per object that gets put in as a string, maybe. But strings in XML can actually do things that are fundamentally unrepresentable in programming languages, which is you can have a piece of string, and then you can have an opening tag and another piece of string and a closing tag. So how do you represent that? So the reason for this mess is, of course, that XML is not a serialization format. XML is a thin veneer of generality around HTML, and HTML is a document markup language. The point of HTML is to make sentences in documents have pretty colors and maybe go blink. And I guess it's usable for that, but it's rubbish as a serialization language for things that are not documents, because it has a massive domain skew with the sort of data structures that are used to describe things other than documents. HTML, and by extension XML, describes the marked up text domain, which is a very different domain from pretty much everything else that XML gets used for, except maybe for images. But yes, so why does this happen? Why are we in this situation? Well, as far as I can tell, I'm not a historian, so this is a lot of guessing here. But it seems plausible to me that what happened is around the 2000s, basically everything was web, and web was the cool new thing. And so if your company wanted to be anything, it had to be web. And the web was HTML. So if you wanted to do a remote procedure call, you basically had to be using HTML. But HTML is, again, not intended for this. So they made XML as the closest thing possible to HTML while still supporting serialization. And this is, of course, not how you design a good format. But I mean, we're here at DConf online. We know that the best tool does not always win immediately. But why has it been 20 years? I mean, okay, I guess 10 years until JSON got halfway popular, but why didn't nobody come up with a better format in the intermediate period? And I don't know. Again, I don't know. And we still see systems coming up and formats coming up that are using XML. And nobody should use XML in 2020. But again, I don't know, and I have a theory. And my theory is that this is actually the fault of XSD. So there's this website. Some of you may know it, Alan Perlis Epigrams in Programming, which is the collected sayings of Alan Perlis, who was, going by his website, a pretty smart dude. Did a lot of foundational work in programming. And one of these epigrams is that data structures induce binding. So what binding means in this context is that different parts of your process are tied together, are linked together by a shared data structure. And so because binding makes your process more coherent, more combined, you should do it as late as possible, because otherwise you're ending up in a situation where you're having difficulty changing your algorithms or changing your approach because your data structure is no longer supported. So you want to structure data as late as possible. You definitely do not want to structure data in your spec phase. You never want to come to a programmer with a spec that tells him what data structures he's supposed to use. Now, the problem with that is structuring data is really, really fun. It makes you feel like you're making progress. It makes you feel like you're contributing. And if you're looking at UML, you will see that structuring data really doesn't need much actual programming language. You can structure domain types as a manager. I don't think I need to say more about this. And so, of course, XSD is intricately tied to XML success, and XSD is also the reason that XML is not forward compatible. What does forward compatible mean here? Well, for example, in JSON, and this was a big pain point that they did specifically because XML did it wrong, you can add an element, you can add a field to a JSON telegram, and all your existing receivers will just go, well, I don't know that field, but so I'm just going to silently ignore it. You can extend a JSON protocol with later versions, and you just throw in more information, and you can even completely change the format as long as the old format is still recognizably in there. And the same goes for protocol buffers. And you can fundamentally not do that in XML as long as your XML telegrams are validated by an XSD on the receiver, because if you add a new field to an XML telegram, all the old XSD specs, which are complete, which have no way to leave out fields, will reject it. Because they say there's a new tag in there and I don't know what that is. I don't know what to do with that, so I'm going to throw an error. So any sort of hope for something like semantic versioning, where you're, for your protocol, where you're adding a feature without necessarily having to do a major release, is out the window. So we at Funkwerk do actually need to talk to an awful lot of external XML interfaces. So Serialized has support for XML. It has very good, very built-in support for XML. And if you're transforming to domain transfer objects, then you can use XML annotations to tell the serializer whether these fields should be subtext or if they should be attributes, or even if they should be text embedded in a tag. But frankly, I've never seen an XML API or an XML protocol that I would say this is good, or this is pleasant to use. And if you use JSON, you don't need this stuff. You don't need annotations to tell the serializer if something is an element or if something is an attribute. You can just throw it on the wire. And so please stop using XML. Okay, rant over. Let's move on. So something interesting is that except for XML, all the protocols I talked about have actually no need for annotations. Well, right now we only support JSON, but sky's the limit, and we're definitely looking at adding protocol buffers at some point in maybe the next few years. At some point, but for now, let's talk about JSON. Now, the thing here is that with DTOs, you still have a lot of overhead. And if you're looking at this code, there we go, sorry. If you're looking at this code and if you're looking very closely at the transform functions, you may note that if we compare this to the very earlier example where we had encode JSON and it returned a JSON value, then the code certainly looks neater, but it's not actually any more simple. If anything, it has gotten more complicated because now we have introduced a transform function and we have introduced a domain transfer object for each of our internal data types. So this is clearly a very unpleasant way to do this, even though it looks superficially clean. And earlier I had an example of an encode function where I returned a JSON value from it. And this is fairly standard, but we've said that we have these DTO types, and it occurred to me a while back that this would be a lot easier if you weren't limited to just returning a JSON value, but you can actually return an arbitrary type from your encoder. And at that point, you would be in a convenient situation where you could, say, for example, you have domain type and you want to change the name of one field in domain type before you put it on the wire. Let's say you wanted to change the field name. And so what you could do is you could just take domain type and you could say to the serializer, I'm going to write an encode function for domain type, and I'm going to transform it into a DTO, but I'm going to do it as a sort of fake DTO where the members in the domain transfer object are once again our ordinary domain types. So let me just change the code a bit to make it work that way. And then what we can actually do is we can go back to using a UUID in our domain transfer object by the same logic, and we can bring back this encoder for UUID, but instead of returning a JSON value, we can simply return a string here, which by the same logic gets recursively encoded and, well, stays a string. And you see that it works. And the big advantage of this is that, hang on, let me bring this up. The big advantage of this is that if we have an internal type that we don't care about changing, say we just wanted to change the name of a field in domain type, maybe we want to change name or something, but we don't care about member type. We are okay with member type being encoded exactly as it is. And so maybe, and then we want to go back to encoding UUID as a string and do that thing. So then what we can do by using this process of going back and forth between with an encode function that returns a domain, that returns a struct of domain types that get passed to an encode function that returns a struct of domain types with a sort of back and forth process, is that we can just cut out one step of the process at any time. Like this. I'm going to show this off as well, because this is, I think, the main value of this talk. And so what we're seeing is that with absolutely no change, our encoding still works perfectly well. We just introduced one domain type, and I'm actually going to change the name field in the type just to demonstrate that this is working. And it comes out correctly, right? So this is pretty cool, because we're getting all the benefit of domain transfer objects, and we're getting it essentially without paying any of the cost. We don't have these trees of encode functions. We don't have necessarily these huge trees of DTOs for every internal type. And it's just, as far as I can tell, the cleanest way possible to do encoding. And we have absolutely no dependence left on JSON values. And so if you just want to make one single change, you just make that one change and then recurse back into your internal data types. So just to demonstrate that this actually works correctly, I'm going to invert it as well. I'm going to add the decode pass, and at the end of it, we're going to get our original data type back out. Okay, so in principle, this should work. And you may have noticed something earlier, which is that our decode functions are templates. And this is actually an absolute necessity. They have to be templates. They have to be an overload of templates because we cannot overload a function by return type. It's impossible in D because it's too hard to disambiguate for the compiler. And so we end up using this template specialization. And what the serializer has to do it has to say, well, I'm looking at getting a field named of type domain type. Do I have a decoder that can give me that field? And because I can't just check if I can call it with that type as I can with encode, I have to check if I can specialize the decode function for that type. And in principle, this works perfectly well. But you may have noticed that we've gotten a very ugly error, which is that it doesn't know. Essentially, what this error means is it doesn't know how to decode UUID. It can't figure it out. And this is weird because we have given it a perfectly valid UUID decoder right there, haven't we? Well, actually, if I'm saying it like this, you can already tell that we haven't. And this brings me to my next part. So let me show you what we did wrong here. UUID, of course, doesn't have a from string method. And if we change that one thing, well, sorry about that. There was about 10 minutes of break there that I've probably cut out where I ran into the same issue that I just tried to demonstrate. And that is caused by the same issue that I'm currently trying to demonstrate, but it works now. And we get the same type back out because we fixed our decode function to just construct a UID instead of calling UID.fromString. And we definitely didn't have any other bugs in it. Yay. Moving on. The problem here is fundamental. The problem is that we have to look if we can instantiate our decode function with a given type, with the type that we're interested in. And the absolutely only way to do this is traits compiles. And anyone who has used lambdas in D before knows that traits compiles is Satan, the great deceiver, who tempts you with ease of use and then punishes you with horrible cryptic compiler errors at a completely different location than the actual typo that you made. So the effect of this is that if you make a semantic error, and by semantic error I mean the sort of thing that is not a syntax error, but this is something like calling a method of UID that doesn't exist, and you make a semantic error in your decode function, then you get a template error in Serialized, and a very cryptic one too. Have you seen, while you were passing lambdas to the standard algorithm functions, have you ever seen no matching overload error? This is that error. This is the exact error. Luckily, there is a better way, and it's can instantiate. If we had a trait that could let us take a template and a template parameter, let's say UID or domain type, and see if the template could be instantiated for that type, in theory, so if the template specialization matches and if the template in condition matches, and then if an error happened inside the template itself, then this error would still be reported inside the template. It wouldn't make traits can instantiate return false. So whereas traits compiles is effectively this horrible C++ thing is FINE. Substitution failure is not an error. This is actually a horrible thing to do, and substitution failure should absolutely be an error. And the only way to get there is to get this error to appear at the point where we want it to. And you may think this is optional, that this is a nice to have, but it is actually essential, because what may happen is that if something that is valid code in one compiler version may become invalid code in a different one, or with a library update or a completely unrelated change, that happens to affect the function that you wrote inside of Decode. And with leaf types, this is not a problem, because you will still get an error at least. But the problem is, if we are using Decode to transform into domain types for structs in the middle of our type tree, then what may happen is that the decode may fail. The decode function may fail to apply. But but Serialized may still have enough information to figure out what it should be doing. And so what happens with that is that a compiler update turns something that should be an error into a silent change in serialization, which is one of the which is incredibly scary. I can tell you, this terrifies me. And as far as I can tell, I cannot imagine that this would be. I'm not very involved in the compiler, but I cannot imagine that this would be overwhelmingly hard to add. And there would be an enormous amount of value, not just for Serialized, but even for every single template where you could pass a lambda in standard algorithm, where currently you have to be very involved with the language in order to figure out what went wrong if you did something wrong, or even how to figure this out. And with this one simple change, a lot of standard algorithm could then be rewritten in order to say, well, I tried calling that lambda, and in principle it worked, but there was a semantic error inside the lambda. So I'm going to print that semantic error at the file and at the line of the actual error itself, and not somewhere deep inside standard algorithm where none dare venture. And so with that single change, the usability of D for intermediate users would immensely improve. So please, traits can instantiate, please add it to the language. It would be so good for all templates, and it would be especially good for Serialized. Thank you, that's all for me. Please enjoy the rest of DConf.